Hi, hello. Can someone confirm whether I'm audible? Am I audible? Hello. Hello. Can someone please confirm? Okay, thanks. Okay, so maybe you can wait for like some 2 3 minutes and then we can start. Hi, so any idea is the other class still going on? Like usually, uh, I mean, like many familiar names are missing actually. Any idea is the other class still going on? Or it's like five of us are here, but generally by this time around 10 people would be joining. So shall we wait for few more minutes or shall we start? Okay, okay, thanks. Maybe we can wait for 2 3 minutes. I think maybe we can start. I think we'll start with the initial introduction, and by the time questions are there, maybe some more people will join. Shall we start? I think we can start. Okay, good evening and a very happy new year to all. I am Prashok. I am doing PhD in IAC Bangalore. So every week during this time, Wednesdays 7 to 8, we will be discussing gate questions in EC, especially in signals and systems, communications, and some topics in maths. So today we will be discussing about some miscellaneous topics in signals and systems. And as so, last week we did not have a class. For that, we'll be having a compensation class tomorrow, 6 to 7 p.m. So let us begin today's session. So today, let us begin by looking at some question on there is echo. Okay, now it's fine. Okay, yeah, I think my I turned on the mic on two devices. Okay, now it's fine. Okay, thanks. Okay, so let us begin by looking at some questions from Fourier transform. So quick revision. Let x of t be a continuous time signal. Then the Fourier transform x omega is defined like this. Here x omega, which is integration. I think we'll let us. So is the other class over or like is it still happening? Okay, okay, thanks. Okay, so we can start. So today we'll be discussing about some miscellaneous topics in signals and systems, and we begin by discussing questions related to Fourier transform. So we have discussed Fourier transform before, but the questions that I'll be doing today are different from what I did last time. So let us begin by reviewing the definition. So let x of t be a continuous time signal. Then the Fourier transform x omega is given like this, like x omega, which is integration to minus infinity, x of t raised to minus j omega t dt. Similarly, given x of t, given x of omega, we can go back to x of t using the inverse Fourier transform equation. So, so the inverse Fourier transform equation is given by like this, x of t, which is 1 upon 2 pi integration from minus infinity x omega e raised to plus j omega t d omega. Now, this is just the basis. We will be moving on to the question soon. So, till now, I think I didn't cover much, but yeah, so we can continue, right? Any questions? By the way, last week we did not have any class. We'll be having the conversation class on tomorrow, evening 6 to 7. Sorry. Okay, so we'll continue. So we'll begin by looking at this question. So this question came in 2014 GATE EC paper. So the question, sorry, GATE electrical paper. So the question is like this. A signal is represented like this. Like we have x of t, which is 1 for mod t less than 1 and 0 for mod t more than 1. Now, given the signal, we need to find what is the Fourier transform of the convolved signal y of t, which is defined like x of 2t convolution x of t by 2. So basically, we have a signal x of t. We have a two scaled versions, like one compressed version and one expanded version of the same signal, and we are taking convolution of those two signals. So we basically need to find the expression for the Fourier transform of this convolved signal. So any doubt in the question? By the way, at any time, if something is not clear, if I am going too fast or if my audio is disconnecting, please interrupt the class and let me know. So we can solve this question like this. So this is one useful fact. So this function that we have, this is known as the rectangular box function. So this will be having the value 1 in an interval from minus tau by 2 to tau by 2, and that will be having the value 0 everywhere else outside. So this signal is known as a rectangular function. So we write this signal as rect of t upon tau. So that means this is a rectangular function having a width of tau. That tau corresponds to the total width with center at 0 and all those things. Now, for this signal, the Fourier transform is given by tau sine omega tau by 2 by omega tau by 2. This is this can be easily computed, but this is a result that is quite useful, so we can use it directly. So this function is also known as the sinc function. Some people use that term sinc for this thing. Now, given this result, let us approach the question. So, what we have? So, we have this rectangular function rect of t by tau. This will be having the Fourier transform 2 by omega sine omega tau by 2. Basically, I just simplified this expression to get like this. Now, we will also see some of other properties of Fourier transform. So, it's like this. Let x1t has the Fourier transform x1 omega and x2t has the Fourier transform x2 omega. Then if we do a convolution of x1t and x2t, the convolved signal will be having the Fourier transform x1 omega times x2 omega. So basically if we do convolution in the time domain, that will become multiplication in the frequency domain. So this is the so-called convolution property. Now with these things in mind, let us approach the question. So what do we have? We have x of t. X of t is defined like 1 for mod t less than 1 and 0 elsewhere. So if we see the function, this will be something like this. There will be minus 1, 1 and the value will be 1. Now going by the notation that we use here, our signal is basically rect of t by 2, not 1, 2 because the width is a total 1. Now, what do we need to do? We need to find the Fourier transform of this signal. I have y of t. This y of t, which is given by x of 2t convolution with the x of t by 2. So let us call this one as x1t and this one as x2t. We need to find. So this is basically x1t convolution x2t. What do we want? We need to find the Fourier transform. So if you do the Fourier transform, you get pi omega, which is the product of Fourier transform x1 omega and x2 omega. This is what we have from the convolution theorem. Now, what is x1 omega? What is x2 omega? We don't know. Let us find that. So this is equal to x of t. Now, what is x1t? X1t is basically x of 2t. Now, what does this mean? So basically, we are scaling this signal in time domain, and in this case, we are scaling such a way that we are compressing it. So earlier, something that was happening at t equal to 0.5 will now happen at t equal to 0.25, like that. Like there's a scale of 2 here. So how do we plot this one? So if x of t is like this, it goes from minus 1 to 1. X of 2t will be going from minus half to half. This is clear, right? Is there any clarification here? This is okay? This is fine, right? I can continue now. Okay, thanks. So the other signal is x to t, which is given by x of t upon 2. And this one is compression. This is basically the expansion, expanded version. We are scaling the other way around. So, and if we plot the graph, it will look something like this. It will be having minus 2 to 2. Amplitude is still 1. There is no change there, like this. So, using the notation that we have, this x1t is given by rect of t upon 1 and x2t is given by rect of t upon 4 using the way we have defined the rectangular function like this. Now, for this function rect of t by tau, the Fourier transform is given by 2 by omega sine omega tau by 2. So, for this first function, I have take the Fourier transform x1 omega will be, how do I have that? 2 by omega sine omega tau by 2 with tau equal to 1. That means this is 2 by omega sine omega by 2. And now for the other signal that we have here, we have x2 omega. In this we take the for a transform. This is 2 by omega sine omega tau by 2. Basically tau equal to 4 here. And this is 2 by omega sine 2 omega. So what do we have? We need to find the Fourier transform of the convolution of these signals. So from the convolution property of Fourier transforms, this required Fourier transform is the product of the corresponding Fourier transforms. So what do we have? We have y omega, which is x1 omega times x2 omega, which is given by 4 by omega square sine omega by 2 sine 2 omega. This I just multiplied this one with this one. That's it. So this is the required Fourier transform, and that means our answer is option A. Yeah. So the correct answer is option A. Yeah. So any doubts, any clarifications here? Shall we proceed further? And if I'm going a bit fast or something, please let me know. Is it okay? Like, shall we continue? Okay, thanks. So, next question. This is yeah, this is related, but it's slightly different. Some more theory is there. So, this question is like this: a sinusoid x of t of unknown frequency is sampled by an impulse train of period 20 milliseconds. The resulting sample train is next applied to an ideal low pass filter with a cutoff of 25 Hz, and the filter output is seen to be a sinusoid of 20 Hz. This means that x of t has a frequency of which of this? So basically, we are given with a sinusoid x of t. We don't know what is the frequency. We don't know what is the frequency, and the question is hello. Yeah. And the question is that we need to find the frequency x of t. What it is given is that this signal is first sampled by an impulse train of 20 millisecond, and then it is applied to an ideal low pass filter. So we have our signal x of t. We first sample it, then we pass it through a ideal low pass filter with cutoff 25 Hz. And we see the output. Let us call this output some name. Yeah, y of t or something. Yeah. Now this output is seen to be a sinusoid of 20 Hz. So what is the actual frequency? Now, yeah. How to? So the question is clear, right? So how do we solve this question? So it's like this. Let us see what happens when we sample a sinusoid. So this is a bit of background theory. So let x of t be cos 2 pi f naught t. This is basically a sinusoid of frequency f naught, simple sinusoid. Now let x of f be the Fourier transform of x of t, the frequency domain representation. So what is happening? Let us sample x of t by multiplying it with an impulse train. Let us call this delta t with period ts. So what it means is that we are having a signal x of t here, which is a cosine function in this case with a frequency f naught. Now we have this cosine signal. We sample this signal by multiplying this with an impulse train. And what is an impulse train? Impulse train is basically a function which is having impulses with a gap of some value like ts. Let us say ts. In this case, we sample it with an impulse sign of period ts. So we have a this is like even though I have shown only like five values, this is continuous. I mean it's there till minus infinity and infinity. The thing is that the gap between these impulses will be Ts. And impulses again, like these are the usual Dirac delta functions. So the amplitude will be infinity, but the area will be one, the usual Dirac delta. Now, when we multiply these things and do a proper sampling, like we need to Yeah, once we do a proper sampling, we'll be getting like this. Like we essentially get the values at these points. Okay, so what happens now in the frequency domain? So we are doing multiplication in the time domain. So in frequency domain, what happens? Convolution. So by the way, is everything fine till now? Like, if there is any doubt or clarification, please feel free to interrupt. So this is what happens in the time domain. We have a signal x of t. We are multiplying that with an impulse train, and this is how the impulse, I mean the sample version looks like. Now, what happens in the frequency domain? So this is a sine wave. So that will be having only one frequency. So this one will be having a peak at f naught. Of course, minus f naught also is there, but that is because of the symmetry. So we have a single peak at f naught for xf. Now, what about the impulse train? So impulse train, we can show that the Fourier transform of an impulse train is also an impulse train. The amplitude is a bit different. Again, we are not worrying much about amplitude today. But the thing is that the Fourier transform of this impulse train is also another impulse train with a gap of Fs, which is 1 by Ts. That's the main thing that we need to keep in mind. There will be some amplitude here. This will not be 1, but something will be there. But for the time being, we will ignore that. We are mostly interested in finding what is the frequency of the signal. So time domain, we do multiplication. Frequency domain, we do convolution. And what do we need to find? We basically need to find the spectrum of this signal, the sample division. How do we have that? We basically convolute this x of f with impulse train. And again, what happens when we convolute two signals? Especially what happens when we convolute a signal with an impulse train? The actual signal, whatever we have, will go and sit around these places wherever we have the impulses. So what I mean is that if you see here, this x-axis, this location impulse will be 0, then fs, then 2fs, minus fs, minus 2fs, like that. So once you do the convolution, this actual shape that is having minus f naught and f naught, this will come and sit here. Like there will be one at f naught, one at minus f naught. So this shape is basically the result of convoluting this wave with this impulse, this single impulse here. Now next, this will be convoluting with this second impulse here, and that will result in the same shape coming somewhere here like this. We have the value fs here, and then there is two impulses here. So this is this fine for everyone? Like, is this clear? This is how spectrum change when we sample a signal. Shall I proceed? This question is a slightly tricky one. So if the theory is okay, then I think that will be okay. Yeah, thanks. So what do we have here? So we have the actual shape coming and sitting here. This one comes here. Then this will come here. This will come here. And everywhere it keeps on repeating forever, basically. So like what will be the values? The values will be like this. That this will be minus f naught and f naught. Then you will be having something at fs minus f naught and fs plus f naught. Then 2fs minus f naught and 2fs plus f naught, like that to this side. Similarly, minus fs minus f naught and minus fs plus f naught here. There will be something here which will be minus 2fs minus f naught and minus 2fs plus f naught, and so on. Now the only thing is that this picture might be a bit misleading. That means we don't know the values of what is fs and what is f naught. So this peak and this peak, they might overlap basically. So that means that this fs minus f naught can be here and f naught can be somewhere over here. So that overlapping can happen. That depends on the actual frequency. So once the overlap happens, it is known as aliasing, and there's a condition for that. And based on this, we derive the sampling theorem and all those things. So for the time being, I am assuming that it's not overlapping, and that is why I have drawn the figure like this. Like this green patch, blue patch, and this orange patch, they are not overlapping. But They may or may not, we don't know. So this overlap happens if this peak goes to the right of this peak. So that's how the green region will overlap with the blue region. So when overlapping happens, we have Fs minus F naught less than F naught or Fs less than 2 F naught. So no aliasing if Fs more than equal to 2 F naught. So this is the usual sampling theorem, the general one, not the specialized one, the usual sampling theorem. Okay, so now coming back, so till now, is there any question? So the key takeaway is like this: if we sample a signal, especially a sinusoid, with an impulse train, the spectrum will contain the frequencies f naught minus f naught, then fs minus f naught, fs plus f naught, and so on. These are the frequencies that will be contained in the output of a sampled version of a sinusoid. That is the main thing that we need to take away from this exercise. So, any doubts, any clarification? If it is okay, we can proceed to the actual question. Like with these things, you can solve the question. Okay, thanks. So let us come back to the question. So what it says, we have a sinusoid of unknown frequency. We don't know the frequency. Now let f naught be the unknown frequency. It is given that we are sampling the signal x of t with an impulse train of period 20 millisecond. That means this value of this ts is 20 millisecond. So what do we have? We have having ts as 20 millisecond. Therefore, the corresponding, this is known as the sampling period. So the corresponding sampling frequency is 1 by ts, which is 1 by 20 millisecond or 50 hertz. So this gap in the frequency domain, which is fs, which is 1 by ts, which is 50 hertz. So for this given question, f naught, we don't know what is f naught. We sample at fs equal to 50 hertz. Now, what do we do after that? It is given that the resulting sample train is next applied to an ideal low pass filter with a cutoff at 25 hertz. So we have the actual signal, then we'll pass to a low pass filter. Low pass filter means what? Like it will filter out everything outside the pass band. So it is given say ideal low pass filter with a cutoff 25 hertz. That means that will be having a response something like this: brick wall response minus 25, 25. Anything outside this region will be 0 and rest will be passed through. So, given this fact, it is also given that the output is having a frequency of 20 hertz. So, what is the actual frequency? Of course, if it is 20 is not an option here. So, it is clear that that is not the signal frequency, it is something else. So, we need to find what it is. So, if you see here the spectrum, basically I'm trying to plot this one with the f naught we don't know and fs 50. So what happens? It will look something like this. So there will be some signal here, some peak here, and also the sample spectrum contains peaks at f naught, fs plus minus f naught, 2fs plus minus f naught, and so on, like on to both sides. So what we need to note here is that out of the many peaks, only 2 peaks are there in this range from minus 25 to 25. And why did I say so? Because it is given that the filter output is seen to be a sinusoid of 20 hertz. So that means after plotting this, like we don't know whether there is this condition or this condition, none of them we know. We have some impulse, some collection of impulses which looks something like this, but there are only 2 impulses in this range from minus 25 to 25. That is the idea. And the location of that impulse is at 20. This is the meaning of what is given in the question. So is this clear? Like up to here, is this clear? Shall I proceed? Can proceed now? Is something okay? Thanks. Yeah. So what it means? So we don't know what is f naught, but we know that the location of these peaks will be f naught, fs plus minus f naught, 2fs plus minus f naught, and the negative versions of the same. Now there are 4 options like 10, 60, 30, and 90. What we will do is we basically try to find what are the possible frequencies if the actual frequency is f naught. So if we have a signal at 10 hertz, that means there will be a peak at 10 hertz. That is for sure. This statement is clear, right? If the actual frequency is 10 hertz, we'll be having f naught 10 hertz. Then 50 minus 10, then 50 plus 10, and so on. These will be the frequencies that will be present in the output spectrum. Now, it is given that only peak in the range minus 25, 25 is at 20. So, 10 is not there. So, this is not the right answer. So, 10 hertz is not the answer. Now, what happens if it is 60? 60 means there will be f naught, that will be 60. But then there will be 50 minus 60, which is minus 10. So what it means is that if the actual frequency is 60 hertz, we will be having a peak at minus 10, which will come somewhere over here, which is again not there in the question. It's not mentioned in the question. What is given in the question is that in this entire range from minus 25, 25, there is only peak at 20. I mean minus 20 and 20. Yeah. Now what happens if it is 90? So this B is wrong. What happens if it is 90? We'll be having a peak at 90, then 90 minus 50, 90 plus 50, 100 minus 90, 100 plus 90, and so. Okay, actually, this is 50 minus 90, not 90 minus 50. Yeah. This is 50 minus 90, 50 plus 90, and so on. Now, again, as we can see here, this is 10. So, if the signal is 90 hertz, we will be also having a peak at 10 hertz, which we don't have. So, this is also not the answer. So, of course, C has to be the answer, but let us see why. If it is 30 hertz, we'll be having a peak at 30. Then we'll be having a peak at 50 minus 30, 50 plus 30, then 100 minus 30, 100 plus 30, and so on. So basically, we'll be having a peak at 30, we'll be having a peak at 20, 70, minus 70. Sorry, this is also the same thing. Yeah, this is 80 and 70. Yeah, we'll be having one at 80, 70, 130, and so on. Now, if you see this, there is a peak at 20, and there are no other peaks like 10 or something like that. There's a peak only at 20. Therefore, that this option satisfies the observation that we have here in this entire range minus 25, 25, peak is at 20. That means the actual frequency is 30 hertz. So the correct answer is option C. This is a slightly heavy question. So any doubt, any clarification here? So the option is answer is C. Option C. Is everything okay, or shall I explain anything once again? Is everything okay? Okay, thanks. Okay, so we'll move to the next question. So we will now see like few questions along the same line. So it's good to discuss them together. So the question is like this. A similar question have appeared multiple times also. So a function f of t is shown in the figure. So this is f of t. Now the question is regarding the Fourier transform of the signal f of t. Basically, we don't want to find the Fourier transform itself, but some property of that. Say function f of t is shown in the figure. The Fourier transform f omega of f of t is option A, real and even function of omega. Option B, real and odd function of omega. Then C, imaginary and odd function of omega. And finally D, imaginary and even function of omega. So basically, given a signal in time domain x of t, we need to find what is the nature of the Fourier transform. Is it like odd, or is it like even? Is it real or complex? Things like that. Now, question is clear, right? I can continue, no? Okay. So to solve this question, we need to know some properties or some useful facts regarding the nature of spectrum, the Fourier transforms. So let us, I will not be proving these facts here, but the proofs will, we'll just discuss these facts here. Proofs will be available in any standard textbook. So again, I think most of you might be already familiar with these facts. So I'm just stating it again to solve this question. So consider a real function f of x. Real in the sense like the function is real. Now, we will first see what is odd and what is even. What do we mean by an odd function and what do we mean by an even function? So, the definition goes like this. This, again, the key thing is that f of x is real. If it is complex, these things doesn't make sense. So, let fx be a real function. Now, f of x is said to be an even function if f of minus x is same as f of x for all x. That means if we have the same shape on both sides on the y axis, like if it is like this, it's like this, symmetry, we see symmetric about y axis, then we say that the function f of x is even. Similarly, this function f of x is said to be odd if f of minus x is minus f x. These are the main definitions of what is an odd function and what is an even function. Now, we have something more. This is the just the definition. So we can make some comments regarding the Fourier transform of odd and even function. By the way, the main thing is that not all functions are odd and even. I mean, there are functions which are neither odd nor even. This is just a subclass. I mean, it's not like all functions have this property. It is more like if the function is odd or if the function is even, we can tell something about the nature of the Fourier transform. That's it. So these two are the results. So how it goes is like this. Let f omega like this be the Fourier transform of f of x. Now, if f of x is an even function, then f omega will be real. So if fx is even, f omega will be real. Furthermore, f omega will be also even in the frequency domain. What it means is that f of minus omega equal to f of omega. This is the meaning of saying f omega will be even. Similarly, if f of x is an odd function, then f omega will be imaginary and f omega will be odd. That's the idea. So there are two things happening here. Depending on whether odd or even, we will be making two comments, whether it is real or imaginary, and whether the f omega itself is odd or even. So there are two statements here in this single sentence. So any clarification here? I just stated some facts. We did not derive anything here. You can continue, right? Okay, thanks. So what do we have here? This function here, f of t, is odd. So if you see here, it is easy to see f of minus t is minus f of t, right? So if we see this point somewhere over here, if I flip the sign to minus t, sign flips, but the value is kind of same. So this function f of t that we have given in this picture, this is odd function. Since it is odd, f omega will be imaginary and odd. That's from the theory. That means f omega, like option C, f omega, Fourier transform f omega will be imaginary and odd function of omega. So the solution is option C. So for this question, we don't have to solve anything as such. It's just that we need to remember the property and apply it. So any doubt or any clarification? Shall we move to the next one? Okay, thanks. Now we will see another question. This is also related. So it's like this: a differentiable, not constant even function x of t has the derivative y of t, and their respective Fourier transforms are x omega and y omega respectively. Then, which of the following statements is true? So what it says is that we have function x of t. This x of t is basically even, not constant. That will become important soon. And I have y of t d by dt x of t derivative. So we are asked to comment on the nature of the Fourier transform of x of t and y of t. So what do we have? X of t is even. So I have x of omega and y of omega. Okay. Now x of t is even. That means what? X of omega is also even and real. That is the property, right? So if the function is even, Fourier transform will be real and even. So in this case, x of t is a even function. That means x omega will be real. X omega will be real. Now that is it. But what about y omega? So there is one more interesting result that goes like this. So if f of x is an even function, which is not a constant, then derivative will be an odd function and vice versa. So that means if we have a function that is even, differentiate that, you will be getting an odd function. Similarly, if you differentiate an odd function, you will be getting an even function. This is another result. And why did they say non-constant? Because if you differentiate a constant, then basically you get a zero. So that's not an odd function. So if f of x is even, d by ds f of x will be odd and vice versa. So the statement is clear, right? Can continue, right? So what it means, this x of t is even function. Since x of t is even and non-constant, y of t is odd. Y of t is not function because that's a derivative. Hence, from the property that we have discussed in the previous question, that if f of x is odd, f omega is imaginary, what we can say is y omega is imaginary. So what it says, x of omega is real and y of omega is imaginary. X omega is real, y omega is imaginary. So this is the correct answer. So any doubts or clarification here? Is this okay? So these questions are like it's mostly like what to say, like it's easy only if you know the property. Otherwise, it will be difficult. But if you know the property, there is nothing much to do. They can directly write the answer. So sorry. So any doubt or clarification? Shall we move to the next question? Okay. Thanks. So yeah, this question again. This is something similar but slightly different. So yeah, it's like this. Suppose x1t and x2t have the Fourier transforms like this. So these are not the signals. Earlier, we are given with the signal itself, the shape of the signal, and we are asked to comment on the nature of its Fourier transform. Now this is like kind of vice versa, but not that same as previous question answer. So what do we have? Suppose x1t and x2t have the Fourier transforms as shown below. So we have x1 omega and x2 omega. Then which one of the following statements is true? Like is x1t and x2t, they are both complex, but x1t times x2t is also complex with a non-zero imaginary part. Is that the right answer? Or like option B, which says x1 and x2 are real and x1 x2 is also real. Or x1 x2 are complex but x1 x2 is real. Or finally x1 and x2 are imaginary but the product is real. So there are three things happening. We need to tell what is x1t, what is x2t, and what is x1t times x2t. So three things we need to comment on. What we are given is x1 omega and x2 omega. So, so yeah. So any doubt in the question? Shall we see the answer? I think we can proceed. So again, so what do we have here? We have the same property that we are using. So if f of x is even, f of omega will be real and even. So how do we say the other way around, like the converse? Like if f of omega is real and even, then f of x is even, right? That's the idea. Is that okay? This statement is clear, right? If f of x is even, f omega will be real and even. So if f omega is real and even, then f of x has to be even. That is not the thing that we want. What we want is if it is not even. So let me write it properly. So what we have. So this is the thing. If f of x is real and even, f of omega is also real and even. This is the direct statement. Now the negation of the statement is like this. If f of omega is not real and even, or at least you can say in a different way. If f of omega is not even, then f of x is not real. You need to be a bit careful while doing these statements. Like it's just not that reading it backwards, but slight difference is there. So if f of x is real and even, then f omega is also real and even. This is there. Now there are two things. There's a real and even both. Now, so what it means is that if the function is real and even, the Fourier transform is also real and even. So if we see here x1 omega and x2 omega, these Fourier transforms are not even, right? This is not an even function. Similarly, this is not an odd function either. This is neither odd nor even, because not symmetric, right? So this function on the right hand side is not same as what we have on the left hand side. Similarly, this thing, this what we have here and what we have here, they are different. So x1 omega and x2 omega are okay. Now it's fine, right? Okay, I think some problem with internet right now. Okay, so what I was trying to say is that from these two graphs, x1 omega and x2 omega, they are not even. That means f of x is not real. That's the conclusion. Why did I say so? So if f of x is real and even, f omega is also real and even. So if f omega is not even, that means fx cannot be real. That's the statement. So this is clear, right, for everyone? Is there any doubt? So I'm using this statement here. If f of x is not even, then f of x is, sorry, if f of omega is not even, then f of x is not real. So both x1 omega and x2 omega, they are not even. Therefore, x1t and x2t are not real. And if they're not real, it's complex or imaginary, we don't know, but let us say complex for the time being, because imaginary also means complex. So therefore, x1t and x2t, this much is guaranteed, like x1t and x2t are not real. So this is not the answer. That is very clear. So the question is that is it option A, C, or D? Like is x1t and x2t complex or are they purely imaginary? We don't know. We need to see that. So till now, any doubt? I can continue. No, I can continue, right? Okay. Thanks. So now I'll introduce another result that will feel like coming out of the blue, but it is useful to solve this. So what do we need to do? So it is given that, so we also need to tell what is x1 times x2. So if you want to see the, if you want to tell whether x1, x2, this product of them is real or complex or even business, we need to know what is the Fourier transform of this guy. Now from the convolution property, this corresponds to x1 omega convolving x2 omega. That's the result, right? If we do multiplication in one domain, that will become convolution in other domain. So to say whether x1t times x2t is real or complex, we need to find what is the nature of Fourier transform of x1t times x2t, which means we need 1 by 2 pi x1 omega convolution x2 omega. So if we have this, if we have this one, then we can tell whether it is real or even whatever it is. So now let us take a step back and see a different result. So there is something known as autocorrelation. Autocorrelation for a deterministic signal. So let x of t be a continuous time signal, like usual one. Then the autocorrelation function is given like this. We define Rx t tau as integration from minus infinity to infinity x of t, x of t minus tau dt. Actually, not dt. This is dt. Yeah. Yeah. So basically, what we do, we try to find the correlation between x of t and x of t minus tau. Correlation like the English meaning, like how correlated they are. So we have x of t and x of t minus tau. This quantity here is known as the autocorrelation. We have integration between t x of t, x of t minus tau d tau. Now, this autocorrelation is having a nice relation with the convolution. So if you do x1t convolution x2t, that is given by minus infinity x1 tau x2 t minus tau d tau. So things look similar, they're not exactly same. Here we have t, here we have t and variable t, whereas here the tau is there and variable is tau, and there is a say kind of flip here. So but these two look related. In fact, it turns out that this autocorrelation can be expressed as convolution of x of t with x of minus t. This is another result that there is a proof for this and it's not very hard, but yeah. So the result is that this term, basically the autocorrelation can be written like convolution of x of t with the x of minus t. Furthermore, there is also another result that says that autocorrelation is an even function. So these are clear, right? The question is still there. Why did we discuss these topics right now? But I'll come to that. So to summarize from here, Rx theta, this is how we define the autocorrelation. And autocorrelation turns out to be an even function. Furthermore, autocorrelation also can be expressed as convolution of x of t with a reverse version of itself. So any doubt in these statements? It's okay, right? Okay, so why did I do all these things? We need to comment on the nature of x1t, x2t. So let us see what are these x1 omega and x2 omega. If we see the graph here, this x1 omega and x2 omega, they are mirrored versions of each other. Basically, they are flipped. So x1 omega is like this. On the right side, we have 1 and 0.5. But for x2 omega, that's on left side. So what we have here is x1 omega is x2 of minus omega from the picture. Also, x1t, x2t has the Fourier transform 1 by 2 pi x1 omega convolution x2 omega. Now, what is this thing? This is same as 1 by 2 pi x1 omega convolution x1 of minus omega, because x2 omega is the same as x1 omega, just that it is flipped. Now, what is this? This is autocorrelation in the frequency domain of x omega. This statement is clear, right? I have this, I just type t is just a variable. I mean, it doesn't matter. I can replace with anything else. Something where I have a signal convoluting with flipped version of itself. Same thing is coming here. X1 omega convolution x1 of minus omega. So this is like a autocorrelation. Now this kind of functions, they are even functions. That is known. So what does it mean? This means that x1 omega convolution x2 omega, this is even, which implies that x1t times x2t is real. That's idea. This is even and this is also even and yeah, that's it. Of course, even and real, so it's okay. Yeah. So this is also, this x1 omega times x2 omega is even. Therefore, sorry, x1 omega convolution x2 omega is even. Therefore, in the time domain, x1t times x2t is also real. Why did I say that? Because of the our original result that says that if the function is even, then the Fourier transform is also real and even. So to conclude, we have already concluded that x1 and x2 are not real, but now we have shown that x1 times x2 is real. So this guy is real. x1 times x2 is real. So what we can say is that x1t and x2t are complex, but x1 x2 is real. So C is the correct answer. Okay. So that's regarding this question. So I think it's already 8. So any doubts? Is there any clarification? Is that okay? Okay, thanks. So I think yeah, it's already 8. So I'm not planning to discuss new question right now. So we have compensation class tomorrow. So next class is tomorrow 6 to 7, not 7 to 8. It's 6 to 7. So we will discuss continuation of this, like signal has miscellaneous topics. So that's all regarding today's class. So any doubt? So shall we? If everything's okay, we can pause for the day. So meeting link, same link, same link, same link. The same link will work. Okay. Okay then. Thank you. Thank you. Thank you very much. Thank you. See you tomorrow. I am ending the meeting. Thanks.